I now hand over to the one and only George Alexandropoulos to lead the panel. George, the floor is yours.
Thanks, Hank. So welcome to this panel. I hope it's going to be of interest to all of you. It has been a long day, very fruitful day, very interesting discussions. And I will go directly to introduce our panelists here, which are actually experts working on the topic, starting with Sami, who is a senior staff research specialist at Nokia Standard in France, with his current focus especially related to ISAC, being on distributed aspects of the physical information for ISAC and its related architecture. Then I will pass to Gabor, who is a master researcher at Ericsson Research, as well as an adjunct professor at the KTH Royal Institute of Technology, Stockholm in Sweden, having authored numerous papers and actually a huge number of patents, many of them related to the topic. We have also together with us Andreas, who is responsible for the major 6D activities of Bosch across different business units and sites. And Andreas, together with his team, he's exploring the potential but also limitations of ISAC in different vertical sectors, including the mobility and industrial domains, serving also as a general chair of 5G ACIA and being actively engaged in the Hexa-X-II ISAC. And last but not least, we have Nuria, who is a professor at the EC department in San Diego University in USA. She's a member of the IEEE SPS TWG in ISAC, co-author of a tutorial on ISAC to appear very soon in proceedings of the IEEE, as well as 2 Best Paper Awards in ISAC-related publication. And she's also a lead editor of another SP Magazine special issue on ISAC to appear very soon. I would like once more, together with Henk, to thank you all for being part of this panel. And let's start with a 5-minute pitch by each of you related to ISAC, and then we pass to the questions being collected. We're looking forward for your fruitful ideas regarding the topic. So let's start with Sami.
Yeah, thanks, George, and thank you for this nice introduction. I think
so let me stop sharing. I guess this is needed.
Yeah. It's fine.
If you want to share anything.
No, I don't have material. I have
some
support later, but in case of the question. But thanks for this nice introduction and for inviting me to this panel. It will be hard for me to discuss after this nice presentation that we got all the day about ISAC and what could bring to 6G. So from my perspective, from my point of view, ISAC in 6G is supposed to combine the power of communication and sensing, which allows devices to simultaneously transmit data and gather information about their environment. This opens an open world of possibilities, like for smart cities, where we can imagine the traffic light that adapts to the real traffic flow, or the autonomous vehicles that navigate safely using environment data. More other application like for industrial automation, like in a warehouse where robots and machines can collaborate seamlessly, sharing data and understanding their environment and surrounding. Other application which is very important for nowadays is the healthcare, where you can remote monitoring system can detect anomalies and provide real-time feedback to improve patient care. So ISAC at the end is not just about faster speeds and better connectivity. It's also about creating a connected and aware world where technology fused with the environment. Yeah, so this is short, let's say, my view about the ISAC and how 6G could emerge. So can give you the hand back, George.
Thanks, Sami. I would like also to ask Gabor to tell us some words regarding ISAC.
Yeah, thank you, George. Thank you for the floor and thank you for inviting me here. So let me start sharing my screen here. I guess at this point, you all see my screen. So I would just like to share some ideas on how we will use 6G as a platform for innovation, utilizing beyond the communication services that we have been discussing today, and to create what we call the cyber physical world. So basically, our vision is that 6G makes it possible to move in cyber-physical continuum, what we call, between the connected physical world of senses, actions, and experiences, and its programmable digital representation. So basically, according to this vision, in the future, the network provides intelligence, limitless connectivity, but also beyond connectivity services that we are discussing today, and full synchronization, full synchronicity of the physical and the digital worlds. So that's our grand vision. We believe that this will create a vast amount of sensors embedded in the physical world, and that's where integrated sensing and communication also comes into the picture. But I also believe that it's somehow instructive, and I'm going to use some part of my 5 minutes to pitch on what drives the Gs and how then integrated sensing and communication and beyond the communication services that we are discussing today in this community comes into the picture. So I believe that G, we should maybe recall that to me, it doesn't only stand for the generations as they are following each other, roughly 10-year intermission between them, but also it stands for global standards. And global standards are very important because that ensures economy of scale for the ecosystem. So, for example, all generations are characterized by some unique business idea. That's my point I'm trying to make, and an enabling technology shift. So the business idea and the technology shift or the enabling technology, they kind of go hand in hand. For example, obviously we don't have time to go through this, but the 2G brought about global roaming and digital transmission. 5G, with 5G, our idea in the METIS project and in the early research phase was that we will create the network society in the Internet of Things. Everything which benefits from connectivity will be connected. And we have been working on enabling technologies, including massive MIMO, cooperative communications, the slice concept, and so forth. So what we believe that 6G, where this business idea and technology shift go hand in hand, is basically the network as a platform for innovation, service programmability, and user centricity. And the enabling technology is one of the key things, maybe, or one of the very promising things, is the full potential of electromagnetic waves, which brings us to the domain of integration of terrestrial and non-terrestrial networks, but also the immense amount of sensors and network as a sensor capability, integrated communication, positioning, and sensing that we are discussing today. So if we look a little bit at what is in the cyber physical world, in this continuum that I'm talking about, well, we see many interesting things. We see merged reality, new ways of meeting and interacting with other people, new possibilities to work from anywhere, but also massive twinning, which implies using the network as a platform for many ecosystems, allowing accurate predictions and detailed control also, and again, the interaction between the digital representation and the physical world. And also situational awareness, so sensing surroundings and locating objects, guiding robots and vehicles with digital maps and so forth. And the final thing I would like just to make one point is that I think we as a community, the research community, the standardization community, the industrial community, we're together here. I think we need to ask the question, not only the technical and the business, but also how we will facilitate return of investment in the network, because that's essential for innovation to flourish. We need to ensure return of investment in network and advanced capabilities, how to foster win-win business models among all the ecosystem players, including the connectivity service providers, chip manufacturers, and the vendors, so that the whole ecosystem and the whole innovation system can flourish. This is what I would like to pitch in my 5 minutes. Sorry, George, if I exceeded the time slot.
No, thank you, Gabor. Thank for this insightful, actually, presentation and questions that you will see that some of them I will repeat later on, which means that I will insist to get some answers from your side. So let's continue with Andreas.
All right, yeah, hello, and thanks for having me. Thanks for the introduction, George, before. So I'm Andreas, and I'm with Bosch, and of course, Bosch is one of the famous vertical players in this ecosystem here. So that means we are a big player in automotives, mobility in general. We are in the manufacturing, industrial, but also building automation and similar areas. So we are in some sense, very much an end user of 6G and what will come with 6G in future. And if you look in general about the potential of 6G, right? So where the big potential is, from my perspective, it clearly is in the verticals. Certainly, the consumer domain will play an important role. That's no question at all. But we have seen it with 5G already, so that the consumer space is maybe not, well, it's already a saturated market. That means there's not so much potential to unlock additional business. So we looked into verticals already with 5G. Maybe we are not where we wanted to be, but with 6G, if we take the learnings from 5G at least into account, we certainly can do very much better from the very beginning. So, and if you look at what can 6G offer for the vertical industries, so I think Gabor outlined it very well already. So that's very much in line with our view. Of course, we will have connectivity, and we will have new flavors of connectivity, which might have to make an impact already, like non-terrestrial networks. On the one hand, providing ubiquitous connectivity, but then also ambient IoT, what we see with both with 5G advanced already, providing very low-end connectivity. But the real exciting stuff, at least what looks very promising from a current perspective, are the new capabilities beyond connectivity. So considering really 6G as an innovation platform, as Gabor mentioned, so digital twinning, AI as a service, edge computing, and so on, and integrated sensing and communication is clearly one of the most promising and interesting topics. Why is that? Because we can do completely new things with it, reusing maybe the infrastructure that we will have anyway for connecting the things. But we see many use cases, and a lot of work has been done in different fora already for mobility, for industrial, for building automation. So all the areas where we are in, be it for traffic monitoring in the mobility environment, maybe extending the field of view of onboard sensors in a vehicle, or in industrial domain, you could create a digital twin of the factory. You could support the navigation of automated guided vehicles and similar things like this. So there's a lot of potential, but at the same time, and this is important, right, that we take the learnings from 5G into account. At the same time, we have to be very careful not to overhype it as well. And to some extent, I think that happens already, so that there's a huge hype behind Isaac. People are very excited, a lot of activities ongoing. But sometimes it seems like we think about a use case that can be done with some kind of sensors, so a sensing use case, and that's automatically an Isaac use case. And to some extent, it's correct, right? So of course, it's very easy to define a use case and maybe also a use case that can be done using Isaac. But not everything that can be done will be done at the end, because it's then technical challenges, of course, but also then business-related challenges, for example, right? So we really have to see what makes sense, what doesn't make sense, how expensive is it, what is really the value at the end, and also what are competing solutions. So it's not that Isaac is the only sensing technology that is around. Of course, there's a very good ecosystem of all kinds of sensors, be it radar sensors, which is maybe the closest to Isaac, but also cameras and other things. And we also have to see where it makes sense from a deployment perspective, for example. So we can do Isaac in a public network, which is needed for use cases like in the mobility space, right? So where we really need good coverage. But there are some specific challenges in the public networks, for example, that we cannot sense everything because we typically need line of sight to a base station, for example, and this is something we usually don't have everywhere. Also, the business model might be a bit challenging, and things may turn out to be much simpler, at least as a starting point, if you look at private networks, right? In private networks, as we have them in manufacturing, maybe in healthcare, in building automation, and so on, because it's a much more constrained environment, it's a much more controlled environment, and also the benefits that we can get from sensing data might be higher if you look at the density of benefits somehow relative to the area that you want to cover. So that's why it's really important to not just do the technical work now, and a lot of technical things are going on, but to really look at the benefits, this return on invest, as we always say, right? So what we really expect here, so that we can see what really makes sense and what doesn't make sense. And then we should only focus on the things that make sense. Also, if you look at standardization and so on, I mean, we really make it very broad now and looking at all kinds of combinations and options, how to do it. The question is, does it make sense? Because if we standardize all this, right, it also gets expensive, the standard gets complex, and the question is what remains at the end. And also this should be a learning from 5G. What we have seen with 5G is a big gap between standards and implementation. And it also led to some disappointment, especially in the vertical industries, because we have seen a standard and the implementation is just a fraction of it. And we really should do better with 6G now from the very beginning. And ISIC is not the only aspect of 6G, of course, but also for ISIC it applies that we should spend much more on the non-technical challenges, on the business-related challenges early on, and not just on technology. Yet, I don't want to end up with a negative flavor, because I still believe ISIC is really a cool thing, and there's a lot of potential. So we should focus on it, but we should do it right. Thanks.
Thanks, Andreas. You will have to elaborate more on the business model. Since it's going to be the first question, actually. So let's pass the floor to Nuria, the sole academic in this panel, to hear her opinion, a general speech about ISAC. Nuria? You're muted. Please unmute yourself.
Thank you.
Excellent. Excellent.
So yeah, I think now the ball is in my side, given that the previous speakers have focused so much on the business aspects. I think I'm going to go back to the research challenges. I think that many interesting research challenges are coming from that view that the other speakers are also discussing of the cellular networks, where we have a lot of infrastructure, a lot of different types of users, and this is different probably from other visions of previous generation networks. So we have to take advantage of that deployment of sensors too, sensors that can be on the user side. Very clearly, automated cars are an example, and then we could have also sensors at the base stations. But we can also have all this sensing capability of the network itself, radio localization, monostatic sensing, bistatic sensing. But we need to look at the whole picture. So maybe the new avenues are like how to do this collaborative sensing, considering all this wealth of sensor data, multimodal sensing, fusing standalone sensors and network sensing. How to do this collaborative positioning, collaborative sensing, distributed in some cases, creating like large arrays with the different elements in the network. So all these things that still remain to be done in most of it. And also a very different feature in future networks is the exploitation of AI. And of course, we need to exploit AI also for integrated sensing and communication. That opens many avenues. We have AI probably at the network level, at the base station level, at the user level. And AI can be very useful to handle different situations. For example, limitations in the models that we are using for joint sensing and communication. Maybe we are neglecting a recalibration in our signal processing models. Maybe we are neglecting errors in the elements in the arrays that we are using. And AI can be an interesting model to overcome all this impact that this has on the performance of the sensing function. And then also we can use ML to handle limitations in our methods. For example, in some cases we need to solve very complicated problems, optimization problems, for example, for designing the informing to be able to allocate resources for the sensing and for communication at the same time, and that becomes really a complicated problem. So maybe data can also help us to do that more with less complexity and achieving better solutions too. And then here is an example where we are mixing, for example, in my group, machine learning and signal processing, I think in a smart way, because this is basically the question that remains. Where should we keep using model-driven solutions? Where should we exploit data? And I think this is an example where we can see that what we were doing for the problem of localization was to exploit the initial aspect, the initial access stage in the communication system is already there. We are going to have a channel estimate, and we can exploit geometric localization initially, and we are going to have an estimate of the position. That estimate probably has a limitation in the accuracy that we can achieve. For example, during initial access, the scenario is very low. We have to exploit multipath. Some of those paths are not estimated very accurately. And mainly the main issue is that we have different estimation errors depending on the path. And if we exploit data to understand how reliable are the different paths to construct that position estimation, we can further refine that position. And that's what we do here. First, geometric localization, then we exploit data with attention mechanism to understand that connections between the different paths that we have and the true position. And then, of course, for position tracking, when we exploit the communication frame to track the channel, obtain updated estimates of the channels, we can, of course, obtain updated estimations of the position. And another place where we could use data could be, for example, for that understanding that temporal evolution. We usually do that. We were doing this before with approaches like Kalman filters and different variations. But there we have the limitations of the model. We need to know all the priors very accurately to make it work well. And in practical scenarios, we have seen, for example, with vehicular measurements that Kalman filter is quite limited. We can see here, for example, that with Kalman, we are able to do this position tracking with the accuracy that we can see with this dashed line. You can see that this is the CDF of the positioning error. And you can see that, well, it's let's say, below 20 centimeters for, let's say, a little bit, like 55% of the users. But if we exploit these attention mechanisms here for temporal evolution and for understanding the impact of the different paths, we can really move to much higher accuracies that you can see in these other plots. So I think the way to go is understanding where and how to exploit data and where we have to keep exploiting models that have worked very well. And of course, another avenue is exploiting all this wealth of sensing data that is coming from sensors, standalone sensors that are already there and will be there, as the other speaker was pointing out. So how to fuse all this kind of information is also very interesting. In my group, we have been doing something related to how to exploit the received signal in a LEO satellite communication system, imagining now that 3GPP is studying and already integrating all these space segments, how the received signal there can also be fused with other mechanisms for positioning, like GPS or IMU. And we are creating these kind of solutions where we mix and fuse standalone sensors with RF sensing coming from the communication network. And of course, a final aspect that I think is very interesting is the integration of the elements in the network for cooperative or distributed sensing. We can think about positioning, we can think about multistatic sensing with distributed MIMO. This is very challenging, of course, because if we look at this as a large array, well, there are challenges to construct those steering vectors related to the synchronization of the phases, stability. We have to know very well the location of the base stations here. But I think from a research perspective, it's super promising because this is really leveraging the whole network. And of course, collaborative positioning is also very interesting. Trying to understand how to really track the position and orientation, assuming we can do it in groups of cars. And this is important because some of the vehicles, for example, for that use case, are going to have line of sight with the base station, but others will not. And maybe we can use this exploit at the same time side links and vehicle to infrastructure links with line of sight, and this can really improve the communication performance. So in general, I think these are aspects that from a research perspective are very promising, all these avenues, and I think we have to keep moving and creating more interesting solutions, and then, well, industry will decide which is really interesting. And by the way, I'm at the University of California, San Diego, not San Diego University, because that is a different one.
Apologies, Nuria. Apologies.
No, just clarifying, just in case.
Apologies for this. Okay, thanks for your pitch. So let me reshare my screen where I've actually put down a couple of questions. Most of them, in a way, have been discussed in one way or another, but hopefully you see my screen right now. But let me try to insist a bit more on them, try to get some answers for you in a more demanding way. So we have been discussing about ISAC, integrated sensing and communication, right? But it seems to me that actually what is actually pronounced is the sensing. So Gabor talked before about network as a sensing platform, as a platform, you said, Gabor, but at the end, as a sensing platform. I mean, one could argue that the discussion is all about this. And I was wondering, what about the other, let's say, version of ISAC, this sensing edit communications, where, let's say, the end buyer of the ISAC technology is not the end user. It's the actual verticals or the network to optimize itself. Having also in mind that on the same side, we also need to provide more rates, and we know very well that there is a trade-off there. So in the light, let's say, of this reasoning that I tried to put down, raised by some people, since we have already some sensor-based solutions that are out there, right? Sensor networks have been out there for quite a while, legacy radar as well. I would like you to elaborate a bit more and try to prioritize the use cases for cellular network-based ISAC solutions, and if possible, to comment on the business model, regulatory aspects, and also societal concerns like privacy and authorization. And let me start with Sami. There is an order on the bottom of this slide just to help us. Sami.
Yeah, thank you, George. Yeah, so concerning, let's say, the use cases, I think we have seen from the different presentation that there was, let's say, a lot of use cases that has been tackled in 3GPP or in ETSI and also in IEEE. But let's say these use cases, let's say, if I summarize, they are, let's say, related to specific, let's say, application or topics, like for intrusion detection to detect for smart home or detect a pedestrian in the highway, other application like support for autonomous driving, or also for UAV detection, healthcare monitoring, like for fall detection. So all this, let's say, all these use cases are certainly related to, let's say, to business model. And I think most of this business model, I would say, is the operator or the service provider who should, let's say, find the right business model. Of course, as a Nokia, as a constructor, network constructor, we can help the operator to find the right business model. But let's say it will be, let's say, more related to use cases. And for example, for the healthcare, I think the business model is, let's say, it's easy to find it who needs this kind of service. Of course, while you do sensing, you communicate at the same time with the person. For the intrusion detection, I think most of the, let's say, people are interested to protect their home. So this kind of service, I think they will trigger or they will guide the business model that will be applied in the future, and maybe will be to emerge in the 6G.
Thanks, Sami. Gabor?
Yes, so my pitch on this is that fundamentally there may be two reasons or two situations in which cellular network-based ISAC solutions make sense. One is when they clearly provide superior performance compared with purpose-built and already mounted sensors. Let me give one example. I think the classical and the very valid example is the cyclist behind the bus. So when we go beyond the ego sensor. So an ego sensor mounted on a car may miss traffic situation in which a vulnerable road user or bicycle is behind the bus. But the ISAC solution, cleverly engineered ISAC solution, can very well detect such a vulnerable road user. So in that case, I think the ISAC solution can provide superior performance. The other situation is when the ISAC solution is inferior in performance, but it brings cost savings for some player. Let me give an example on that. I recently learned from colleagues working with traffic light control in Stockholm City that we already have good engineering solutions for traffic light control, and they are surrounded with a bunch of sensors, lidars, radars mounted on rooftop, or certain type of coils mounted under the road surface. And those work well. It's just that the maintenance of those, the upgrade of those are very tedious and costly. So in that kind of situation, an ISAC solution can actually complement or even replace much more effectively that kind of situation, because it's not that demanding to detect a car. And paradoxically, this example is also a good example for certain environmental situations in which the ISAC can actually provide superior sensing performance. And that's, for example, in the nighttime, when maybe radar wouldn't work that well, or in a winter situation, and so forth. So I think that it's very instructive actually to look at what purpose-built sensors there are out there, because they are already maybe in small scale, maybe in larger scale, give us an indication on what business models are actually flying today. And such use cases and scenarios we find in the manufacturing industry, including the process industry, in automotive industry, immersive interactions, maybe in future more work, gaming, retail, also public safety and defense industry, and actually the railway industry. I learned recently that the railway industry is investing heavily in purpose-built sensors to detect objects on the rail, because they can cause severe accidents. But also ports, construction, mining, controlled environments, and also explorative like healthcare, agriculture, and the unmanned area vehicles and the digital airspace, detecting drones, for example. So all of these, I think, are examples when ISAC is either inferior in performance but cost efficient, or actually superior in performance.
Thanks, Gabor. Andreas?
Yeah, I think, of course, that's really an important question to answer. So that's why I'm grateful that you put this first here. And from my perspective, there might be different cases, right, where ISAC really makes sense. So one example is that if we manage to standardize this in 6G, and we make sure that it really will be one global 6G standard, which from the current perspective will be the case, right? Then you could assume, okay, suddenly you maybe have sensing capabilities all over the world. You know to some extent what the sensing system can deliver, and you know to some extent how to consume the sensing services. And that makes it a very powerful platform again, right? So because then I can develop a use case, an application, and no matter whether I'm providing it or using it in China or in France or in Canada, so to some extent, I might be able to know what I get. Of course, there are different frequency bands and so on, right? The devil is in the detail, but still it's somehow a standardized sensing solution that is available globally, which has some benefits. At the same time, so then, of course, we have a lot of sensors in place today. If you look at mobility scenarios, a modern car has quite a number of sensors and very good sensors. Will ISAC be as good as a automotive radar? Most likely not, right? So there are very good reasons why this will not happen or cannot replace automotive radars. But at the same time, a base station, for example, has a special location, right? So in a car, and it goes in line with what Gabor mentioned with the bus and the vulnerable road user, right? A car sees what is around the car. A base station mounted on the rooftop or on a special post and so on, of course, has more a bird's eye view on a certain scene. And this gives you then some additional information, even if maybe the resolution and so on is not as high as the one of a classical radar, but it still might be useful in different scenarios. But maybe the most relevant promise from my perspective for ISAC is that it may lead to convergence. And this applies maybe even more for private networks than for public networks, right? If you look at the factory of the future, and if we assume we will have a 6G, 5G, 6G network anyway, we're still working hard on this, but I'm confident that we will be there one day. And if we then have this network anyway, and if we can get more features, more functions out of the same infrastructure that we will have anyway, right? So that we can reduce the complexity, the heterogeneity of different systems that we have to set up and that we have to manage and to operate. So this also gives us some benefits. So it reduces complexity, can bring the operational expenses down and so on. And that's why convergence and this idea of having a platform certainly is very powerful for ISAC in general. Having said that, so of course, we always have to recognize there will always be alternatives. So I think it's probably there's not a single use case that cannot be realized differently. And that's why we should not only focus on, okay, does an ISAC system make sense and how good is the performance and so on. We always should look at what are the alternatives out there, right? An alternative could be I can develop a base station that can do sensing at the same time, deploy it, works very well. But I could also just maybe put a camera next to the very same base station, right? So a camera that is readily available, don't have to develop anything more or less. And I somehow even use it for sensing assisted communication. So I use the camera signal to enhance the communication system and so on. It's maybe not so exciting and not so much rocket science, but at the end of the day, it might lead to a better value proposition and a better return on invest than having this very deep integration. And this is what I also wanted to outline in my initial statement before, right? So we should look at these things early on and really get a good understanding so that to make sure we really focus on the sweet spots and on good solutions for real world problems. And maybe just to add on the second part of the question, if I may, so which is more the business models, regulatory aspects, and so on. I think also this is super important, right? And regulatory aspects a good example for that, because currently spectrum is allocated either for communication or for sensing, right? It's either a mobile service or it's radio determination. And at least to the best of my knowledge, it's always like this. And the question is then, to what extent can I do radio determination in a band allocated for mobile service and maybe vice versa? And you could argue, okay, maybe to some extent we are doing this today because we are doing channel estimation, which is some kind of sensing as well, right? But if you then have the other extreme and say, okay, I use now my 6G network just for sensing and not for communication anymore, most likely they will not be allowed. Yeah? And then the question is, where is the borderline? So how much sensing can I do in a future 6G band and whatnot? And also this is important to understand early on, because otherwise we may end up developing a great system that can achieve a great sensing performance, but the regulators say, no, it's not allowed. And then would have been a waste of effort and resources. So that's why especially these non-technical challenges are super important to societal concerns as well. Maybe just the last comment I want to make, and also this is something to be taken seriously. We have seen a lot of resistance in some regions, at least in some countries, with the introduction of 5G already. Right? I remember some headlines where it was claimed, okay, 5G is killing birds, or people feel uneasy because a new 5G base station is put up and so on. And you may say, okay, that's nonsense or not. So that's in the maybe eye of the observer, so to say, but there are concerns. And we have to take these concerns seriously, right? And there will be even more concerns. I'm convinced about this if we tell the general public, okay, a mobile network in future can sense what is happening. They might even track people, right, by doing sensing, not just the one snapshot, but more on a continuous basis and so on. And of course, you can say, okay, we make sure from a technical perspective that the information is not misused and so on, all fine, but the concerns are still there and we have to take them really seriously. Otherwise, there might be resistance in the public. And also this may lead to a scenario where it's very hard then to introduce these things in practice. There are certainly regions where maybe it's easier to come up with these concerns than in others. I mean, I'm from Germany. In Germany, we are very good at having concerns and complaining, which also has good sides, of course. But this is really something, that should be taken seriously. And I think what is needed for that is really transparency, right? And establishing a dialogue with the general public in a way, understanding concerns that might be there so that we can also address them early on.
Thank you, Andreas. So, Nuria, your opinion on this, let's say, not very academic question?
Yeah, to me, the clear advantage of ISAC solutions is exactly the networked sensing. I mean, you can have a very good standalone sensors, but what they can sense is limited by the line of sight, basically. So the ability to be able to have many sensing elements that are already connected, that are already communicating to each other is huge to me, because it is exploiting that collaborative and distributed sensing capability I was discussing. And I think maybe so far the research has focused more effort on understanding how to do monostatic sensing with a base station, how to do biostatic sensing, but this network capability has not been studied completely. And even if you think, okay, but I'm imagining, for example, connected vehicles, since the vehicles already have each one of them radars, in a way, the standalone sensors could also communicate to another car what is seeing. But the thing is that also introduces an additional latency. So because you need the communication between the sensor and the communication module in the car, while if the sensor is doing as a byproduct of communication, that latency component disappears there. So I think it can be faster and reduce latency. And of course, this providing this view, this complete view of a given area with all this information. I don't know if you want to discuss now this comment you were making about sensor-aided communication, or later. I lost there.
I would like your comment here regarding that. How much you believe on this? I mean,
yeah, I mean, my group started to work on radar-aided communication in 2016. We had our first paper there, and has been quite active on this idea of sensor-aided communication. First, we did it with exploiting standalone sensors, in this case, automotive radar. There are other groups that later have been doing things related to camera-aided communication, and the problems we can address are very different. We can use sensing information to reduce beam training information, or we can use all this sensing information that we are going to have about the environment to speed up the channel estimation, to really come up with a first prior about the channel, because it really, we have a very good idea of the propagation environment if we are doing mapping, if we are finding all the scatterers in the environment for sensing applications. So we can really reduce this bottleneck that is always in MIMO networks, which is the channel estimation overhead. We can do things related to the design of beam codebooks that are adapted to different locations. In many locations, if we use a standard codebook that has beams pointing to every possible direction, no matter where we use the codebook, that's not really adapted to the environment, because we know that many of those beams maybe will never be used. They will never point to other users, because there will never be either users or targets in a specific direction. So creating all this adaptation in the network with the sensing information is very important. In this tutorial paper that is already now in early access, we have a section that discusses all these ideas on sensor-aided communication, and I think is very interesting, but probably farther from the standard. I don't think industry has still understood the potential of all these blockage detection, reacting proactively to blockage if you know where all these mobile targets are and how they are moving, how they can block in the next frame they are linked. So this is really very powerful, but not exploitable.
Yeah, thanks, Nuria. Let me proceed a little bit to another question, which in a way, it seems that the first part of it, you provided an answer already. So I'm changing a little bit now the sequence of the answers. And now I would like to ask you all about, what's you believe is going to be the role of AI ML versus conventional estimation approaches, or even using hybrid kind of approaches, and when to consider each of these approaches with respect to the use cases that we said before, the frequency band related to this use case, if it's going to be actually indoor, outdoor, in low or high mobility, etc. And having said that, I would like also your comment on enabling technologies to do that. I mean, what's your opinion about utilizing smart wireless environments through reconfigurable intelligent services, full duplex for monostatic, etc.? And just to complement this question, what levels of integration at the end of the day of sensing and communication you see to be viable? And I would like to start with Gabor and try to actually to ask from you all. Let's stay in 2 minutes your answer in order to make it for another couple of questions. Gabor, please.
Okay, 2 minutes. So let me start a little bit with maybe the last part, the level of integration, and also some other very closely related, what I call design aspects of ISEC systems, because I think that these are related to all three questions. So of course, in the community and right here in this workshop, we have been discussing the integration, what I call the integration aspect. So this has to do with what level of integration we have between communication and sensing. And I'm not going to repeat what, for example, Hank also showed in his slide. So we can talk about application level, spectrum level, hardware level, full integration. But also there is another aspect, the topology aspect we have been discussing, so I'm not going to repeat it. But there is one other aspect which is maybe less often explored or discussed in this content. That is what I call it the node aspect. So the node aspect has to do with whether we are talking about, when we are talking about integrated sensing and communication and joint communication and sensing, are we talking about joint transmitter? And that imposes certain type of constraints, and that has actually been explored pretty much in the academic literature. I mean, what are you, George, you yourself refer to the trade-off between communication performance and sensing performance, but is it due to because we are using the same transmitter for transmitting communication signal and the sensing signal, or is it so that the integration takes place on the receiver side, and there the sensing signal causes interference to the communication signal, and the communication signal causes interference to the sensing signal, or both? So I think that is important, and especially there is this famous, or shall I say infamous trade-off associated with integrated sensing and communication, and that is the so-called deterministic random trade-off. The deterministic random trade-off is very important because on the one hand, for communication purposes, we would like to have, if I may express myself a little casually, as random signals as possible, because for capacity achieving, we need Gaussian signals or random signals. On the other hand, for sensing signals, we would like to have deterministic signals because they are good for exploring the environment. So there is an inherent trade-off there. And this kind of trade-off we have been exploring for 20, 30 years for communication in the context of pilot data trade-off, right? We have been exploring, and the community has been exploring how much resources in time and frequency we should put on the pilot versus the data. Now we have to decide, okay, how much of our resources we should put on sensing and how much on communication, because of the transmitter side constraints and because of the receiver side constraints. And I think all of these things can be investigated with models and with data-driven approaches. So I think that all of these things come together. The level of integration, is it on the networks, is it on the transmitter side, or is it on the receiver side? And also whether we use deterministic signals like we use for pilots or whether we use random signals. In a recent paper, actually, we showed that with random signals, you can do sensing, but your camera bounds will be higher. So you pay if you use random signals for sensing, you can do that, but there will be a performance price. And so these kind of things, I think, can be explored with AI/ML and all what we have at our disposal as a research community. Thank you.
Thank you, Gabor. Andreas.
I will try to keep it short because I took maybe a bit more time in the previous question. And I'm also not the one maybe being as deep in the technology as most of the other panelists here. What I just want to say is I think we really should start small, right? So we should not aim at starting with a fully integrated JCAS system as listed by RIS, monostatic sensing with full duplex and so on. So which would be the high end and maybe the most advanced system at some point in time. But I think it's very unlikely that we, from where we now are, right, transition then to such a high-end system immediately. So we should really start small. That means look at more or less the simple system that we can think of that can integrate sensing somehow, but it still provides value, right? And that is easy to deploy it. And I think that's the art of finding these small steps, and each step can be a bit more advanced and so on. And then at some point, we may end up with this high-end solution and so on. But with many of the things that you listed here, right? I mean, RIS is a cool topic. We also are a member of the Instinct project, for example. We're looking into this, but it's, of course, also many question marks with RIS, right? Technical ones and also non-technical ones again. Who's operating this and things like this. The integration level should not be really deep integration at the beginning, or maybe switching, or maybe even just putting sensors next to communication devices and so. And full duplex, of course, is manageable somehow, but makes things expensive, right? So it makes it then again more difficult to come up with a business case. So that's why maybe bistatic sensing or quasi-monostatic sensing, so putting separate transmitter and receiver just next to each other might be the easier way. So I think that's the really important recommendation. Start small, think about these small steps. That's the keys to success. From an academic perspective, it's always more exciting and interesting to focus on the most advanced system somehow. But the most impactful system will be the ones that then make it also into practice.
Thank you, Andreas. Nuria, although I believe you answered the first part of this question already. Oh, sorry.
Yeah.
Yes, Nuria, it's you. Yeah, Nuria.
Yeah. See, for the first one, I'm not going to say much more. I already in my presentation discussed a little bit about this. Regarding full duplex and RIS, I think the main limitation is that, well, it's not really considering to the standard yet. It's not a technical concern. It's not a technical limitation, but full duplex circuits are still not commercial and are still not part. Full duplex communication is not part of the standard. So to me, that's the limitation. There are still people trying to design effective full duplex circuits. It's an interesting line of research. So maybe it's farther from the possibility of being implemented, this kind of monostatic sensing using a full duplex circuit. And then regarding what is possible to integrate sensing and communication, I have to disagree a little bit about this opinion that we have to split so much the resources between communication and sensing. The communication system is already doing sensing when it's doing the channel sounding. So to me, it's more like how can we enhance that channel sounding stage to perform a better sensing? But I don't share that vision of having to split the resources and using different waveforms for sensing and comm. It's just maybe because of my background on channel estimation, I can see so well that estimating the channel parameters is giving us so much information about the environment. The limitation is that for communication, maybe you do not need so much accuracy on the channel parameters as you need for sensing. But you could really put more resources on that stage and do better without a huge difference in performance for communication. So that's how I see things.
Thank you, Nuria. And Sami?
Yeah, I think all the panelists have mentioned this, that let's say with the increase of all the devices, let's say that is meant for sensing, let's say we first should start, let's say, small by small, and then we increase the complexity and once let's say the sensing complexity could not be solved by let's say the classical approach. In that case, maybe the AML could be a solution to tackle this corner case where, let's say, for example, like for the resource allocation or for the spectrum sharing between different entities. In this case, there is, let's say, some adjustment or some, let's say, some gap to fill with the AML. And especially also when we have the RIS deployment, it depends on, say, who is pushing RIS or not, but also this kind of technology is, let's say, essential, let's say, to cover the blind spot that the classical sensing technology is not capable to perform. But in that case, this, let's say, the complexity that is brought by the RIS need to be solved also.
Thanks, Sami. I know we're heading at the end of the time that we have for a panel, so I would like to go for, let's say, this question to be the final at the end of the day. 1 minute should be enough for everybody. trying to identify here the key design options for network-based ISAC in terms of the functional distribution between the UE, architecture-mounted and on-board sensors, and the sensor network. So we need to understand what are these design options to which you believe more. And I would like to ask you about the potential and the challenges of distributed and cooperative ISAC, right? Mono or multistatic. I mean, there are many questions here in this family of questions. Choose what you would like to answer in 1 minute, please, because Henk is keeping the time. So let me start with Andreas.
Okay. Guys, indeed, many questions, but maybe I focus on the last one, right? So, and I briefly touched this already in the previous question. So I think if we look at, should it be monostatic, should it be bistatic, should it be multistatic, and so on, we also have to look at the practical implications, right? And monostatic sensing in the base station means I can only sense what I see. Unless you have some tricks to sense around a corner and so on, sensing relays, of course, there are some advanced things that are being discussed, but it makes it then again complex and so on. You can only sense as a starting point where you have line of sight. And the question, where is this the case, right? If you look at a city center or so where do I really have line of sight to a base station? Or if I look into a more rural area, so this really limits what you can do. Again, in private networks might be a bit easier. If you then look at bistatic sensing, somehow some things get easier, right? Because we don't need full duplex, so that's then nice. But we didn't then line of sight to 2 base stations at the same time. And that's, of course, then even more challenging, right? So where do we really have line of sight to 2 base stations at the same time? And unless we have, again, some tricks, it will not work otherwise. So that's why I really think the best starting point might be quasi-monostatic sensing. So having just one base station or one device, right? It is sensing and transmitter, but separate devices so that we don't need full duplex, which again adds to the cost and so on. But we have to carefully think about where to deploy it, how to deploy it, and what we can then do with it at the end.
Thanks, Andreas. Nuria.
I would like to talk about these potential and challenges of distributed cooperative ISAC. I think this is a super promising technology, but it's still starting. And the potential is that you can have this multi-view aspect of the objects, and the challenges are more related to the synchronization of the measurements, which is something that is challenging. But I really that is what gives the full extent a full extent of exploitation of the capability of the cellular network as a sensor. Really, when we are putting all the elements in the network to operate together. But yeah, challenges related to synchronization of the measurements. Yeah, I mean the methods are different. I mean, how to consider synchronization in different aspects, not just the time aspect. We also need to consider different orientations of the arrays that the users are going to have, different orientations with respect to the base stations. All these things introduce uncertainties into the measurements, and we need to be able to solve this technically.
Thanks, Nuria. Sami?
Yeah, so let's say that the purpose of multistatic is to take advantage of the available resources and available devices like UE and G0B enabling, so to perform sensing. And this sensing results could be later gathered and exploited by the SMF to perform some data fusion or specific target. So let's say multistatic sensing or distributed sensing is, let's say, the best way from my point of view, but of course it will depend on the use case and the complexity that you can handle. So of course, monostatic, you don't have this kind of problem, synchronization problem due to the collocation of TX and DX. And the bistatic, you need the synchronization aspect if you need to do some radio wireless imaging. So actually, it's mainly depend on the use cases. Of course, the distributed sensing brings some more diversity, so you can have a multiple angle of view of the same targets. So it's a big issue, and I think a lot of let's say research need to be done here in this case.
Thanks, Sami. And Gabor?
Yeah, so I would just like to recall maybe two lessons learned from 5G positioning, not for sensing because we didn't have sensing in 5G, but maybe it's useful to recall. And the first one is that in 3GPP we did standardize positioning reference signals and SRS sounding reference signals for positioning, but those were not really used. And the TRS, for example, was never really used or never really interested for MNOs because it took away some valuable spectrum for communication services. So that we need to maybe recall. And the other one is that the problem with full duplex or the monostatic sensing is not just the single node full duplex problem, which is a huge problem in itself. But I know that in a point-to-point session, in proof of concepts, it has been demonstrated to work to some extent. But the big problem is on the network level. So the big problem has been already in dynamic TDD, the base station to base station problem. So when we are talking about monostatic sensing on the base station level, not only that we would have to solve the monostatic full duplex problem on the node level, but we would need to address that on the network level. So in the light of this, I think that a promising approach is involving the UE, but maybe combining things with positioning, because we probably need to know the position of the connected UE in order to make sense of the UE as a sensor, as a bistatic node, either as a receiver or a transmitter. So I think that's where our design will have to combine positioning concepts and positioning results and the sensing results in the bistatic sensing. That would be my 2 cents on that.
Thank you, Gabor. And in the economy of time, I would like to close this panel. Thanking you once more for sharing these insightful opinions regarding ISAC, and pass the floor again to Henk for closing this wonderful workshop. Thank you once more. Thank you.
Thank you, George. As we conclude today's panel discussion, we reach the end of what's been an intense and enriching day centered around integrated sensing and communication. I hope you found the sessions as inspiring, instructive, and insightful as I did. I certainly learned a lot. And I want to extend my sincere gratitude to all of the speakers for their enlightening presentations, to the panel members and the moderator for their active and thought-provoking discussions, and of course to you, the audience, for your participation. We had over 75 registrants today, so the level of global interest in this field is clear and truly engaging. Thank you very much and have a nice day. Goodbye.